Hello. Today I'll be proving that, let's say there's two infinite plates that run like this, and one is a positive plate and the other is a negative plate. And this is infinite, meaning it's infinite in the y direction, it's infinite in the x direction, it's infinite in the z direction. Wait, no. No, actually, never mind. It's only infinite in a plane, alright? So only in the x and y directions, I guess. And they're parallel plates. I want to prove that wherever the particle is, it will experience a constant force. So if it's over here, it will experience a force of F. And let's say this is a proton. If the proton's here, it will experience the same force of F. It doesn't matter where it is. This proton will experience the same force. And yeah, alright. So let's begin proving it. So to make the calculations easier, let's just say both of these plates have the same charge density. Or no, it's not exactly dense. Okay, let's just call it charge density. So we have a proton here, there's a positive and a negative plate, alright? And let's call the charge density rho, and rho would equal the charge total over, well, the area total. And let's just make this pi r squared. So just think of a circular disc that expands infinitely. This thing, the thing I've just explained before, only works if both of the plates have infinite charge and infinite area. So Q total, charge total over pi r squared total, all right? Now, let me redraw it. Let's start defining some things. Let's call this distance here from here to here d, and let's call the total distance big D. So that means this distance from here to here would be d minus d, all right? And let's we want to find okay, so here's my thought process. There's a charge here. We want to find what force that this charge at this position exerts at this on this charge. So, all right, so let's draw a line like this. So we know this distance from here to here is d, and let's call this distance the variable r. We're gonna vary r in our integral. That means this distance right here is r squared plus d squared by Pythagorean theorem, or distance formula, r squared plus d squared root, all right? So what's the force? Well, force equals K Q1, Q2 over d squared. But however, there's a stipulation we have to make. Since there's also another particle exerting a force like so on a proton, these two particles have x components which cancel each other out. So we should only look at the y component, because if we put a particle in a plate here, it won't move to the side, because the side cancels out. I hope that makes sense. So we're only looking at the y component here. So what would the y component be? Well, sine theta times root r squared plus d squared, where hypotenuse times sine theta would equal the y component. What does sine theta equal? Well, sine theta equals, well, if let me think here. All right, so this is theta, then sine theta would equal d over root r squared plus d squared. All right, so if we multiply sine theta plus that, we just get that, let me think. I think I messed up somewhere. Whoops, my bad. Wait, never mind, yeah. Okay, what we're looking for is sine theta. All right, so we're looking for sine theta, all right? And we need to multiply sine theta to this force here, because we only want the y component of the force. So sine theta force equals this times sine theta, all right? But furthermore, we need to look at exactly what these charges are. Let's call Q2 this charge right here, the point mass, and let's call Q1 the charge on this plate, all right? Something I want to do is I want to split this plate up here into multiple circles. So if we take a bird's eye view, so we're looking at from the top, we can see that this plate is made up of multiple circles. And yeah, so I want to find an area of one of these circles. So, or yeah, okay. This would be, it's not a good drawing, but okay. I want to find the area of the shaded region in right here. So we'll make the width of this ring here dr, so that would be dr, and obviously the circumference would be 2 pi r. So this area right here would be roughly dr 2 pi r, and this gets more accurate as dr approaches 0. So we know the area of each of these rings, and we also suppose that there's a uniform charge density or charge over area. So one ring, how much charge would one ring have? Well, the amount of charge one ring would have would be the uniform charge density times its area, which would be, in this case, 2 pi r. All right? I hope that made sense. Okay. And what would this equal? Well, this would equal Q1 in the equation. Remember, we said Q1 is the charge on the plate, and we split this plate up into multiple rings. So this would equal Q1. All right? This equals Q1. And then we multiply by Q2 to get the force. And so we have a new equation. Sine theta F equals, well, this is Q1. So K rho dr 2 pi r times Q2. And for this distance right here is actually root, I think, r squared plus d squared, because the distance from this ring of charges. So I split this plate up into multiple rings. Each particle on this ring have the same distance to this point here. I hope that should sound intuitive, that each point, we split this plate up into multiple rings, and each circular ring, each point on the circular ring has the same distance to this point here when we take a bird's eye view, all right? And that specific distance would be r squared plus d squared root, all right? And it goes with this charge equation. So we have this, and then what did we say sine theta was earlier? We said sine theta was d times d root r squared plus d squared. All right, and we simplify this down to, well, look, the squares and the root cancels out. So if we multiply this and this, we get this. Let me show you. We get this. We get a cube type, or not a cube, or 1.5. All right, and now we have a formula for a formula of charge versus radius, and now we want to take an integral. So look, this radius represents the, okay, lim is rt approaches infinity. So we thought of these plates as two discs, right? And these discs are have infinite length. So that means the limit of this integral we're taking here would be to r total. And from 0 to r total. So it would be from 0 all the way to r total, all right? dr. All right, oh yeah, we also forgot about the bottom equation here. What would this bottom force look like? Well, it would actually look really similar. So this distance right here is d minus d, right? So this bottom part right here would be an integral of the 0 to rt, and there's very few things changed. So it would be this. And this d right here would become, well, let me think. It would become d minus d, or big D minus d. over, well, instead of d squared, it would be r squared plus d minus d squared to 1.5. I hope this makes sense, but yeah. All right, so let's focus on the integral of this. What would this integral be? Let's simplify it down. So let's take out the constants to the front. So 0 RT, it would be k rho 2 pi q2 and d. All right, these are constants. So we're left with pi. We're left with r dr, r squared, and this is an easy integral. This integral just equals, or 0 to RT, let me think, root r squared plus d squared and 1. You can check this integral yourself, but yeah, that's what the, wait, let me think. Yeah, this should be the integral, or negative. Yeah, forgot the negative sign. All right, and this just becomes, well, if we take into account the negative here, it would actually be this minus that. So it would be 1 over root r squared minus 1 over rt squared plus d squared. And let's rip this page out, start a new page. All right. So yeah, we can't forget these constants here. So let's rewrite the constants. That's a little bit too high. K rho 2 pi q2 d. And we have right here, wait, no, whoops, my bad. It should be 1 over d squared. We plug in this 0 here, and this negative sign, flips it around. So 1 over root d squared minus 1 over root rt squared plus d squared. All right. And lim, remember, we said we want the plates to be infinite. So lim as RT approaches infinity. All right. And look, this RT approaches infinity. You'll start to notice that this just becomes 0 because 1 over infinity is just 0. So we're just left with this. And let's just take out the root. And these d's cancel out, and we get kq 2 pi q2 for the force that this top plate exerts on this particle here. But what about the bottom plate? What force does the bottom plate exert on this q2 charge here? Well, it's a very, very similar process. So basically, if we take an integral of this, we just get the same thing. And you can try this yourself, but we get that the final answer equals kq 2 pi q2. If we take an integral of this, this is what we get. And you can take the integral yourself. I'm not going to do it here. I just want to, be done with this. Oh, that's my hair. All right. So if we look at this plate here, this is a proton, right? So this positive plate is pushing down, and this negative plate is also going this way. So we add these forces together. In the end, we get 4kq pi q2. All right? And kq? No, k rho. Whoops, my bad. I transcribed it wrong. So this should be rho. And what does rho equal? Rho equals charge total over pi rt squared. So our final answer was, if we substitute rho, be 4k. These pi's cancel out. And 4k charge total times q2 all over rt squared. Oh, but you might object that this rt squared approaches infinity, therefore this equals 0, but that's not the case, because qt is also approaching infinity. So yeah, qt is also approaching infinity. So infinity over infinity, we can't solve that, but infinity over infinity could be a constant, all right? And I guess what we're trying to find is a formula for the electric field. So basically we just divide by Q2 because F over charge equals electric field, or just E. I think that's the variable for electric field. So electric field would equal 4K, the total charge, over the total R squared. All right. So so these are all constants. The total charge is a constant. The total radius is constant. K is constant. 4 is a constant. So that means that the force on the charge here, or the electric field, does not vary within any point in here. So any point, the force on a charge of a certain charge, or a charge of a certain charge, would experience the same force, right? And this is a proof of it, because the electric field is a constant. It does not vary with any variable, because these are all constants. Thank you.